Hey guys, I'm going to be giving you a spotlight talk on damage reduction via a white box failure shaping. So, an introduction to post-deterministic software engineering. First, we need to understand what the basic core principle in software engineering was and what it is now emerging to be. So, traditionally, software engineering was built on the assumption that the hardware that is provided will take an input X and will reliably give you an output Y under all circumstances, basically. Coming to present day or a little bit newer hardware, the focus is more on resource savings and energy savings compared to reliability. So therefore, a deterministic execution cannot be assumed at all points. This shift presents a significant challenge. So we need to ensure that software remains correct and functional even when the underlying hardware is unreliable. The importance of this research is based on the fact that it is inevitable that energy efficient hardware will come into the picture more and more now since we're moving towards that. So there will be a sacrifice in determinism. It is also critical in high performance computing areas where even small errors can have significant consequences on the output. So there is a need to handle methodologies in non-deterministic execution and scenarios. Coming to the overview, the authors have introduced the concept of failure shaping, which basically aims to reduce the damage caused by hardware failures by strategically reallocating them. The researchers have developed a tool called the Criticality Explorer. This uses Monte Carlo simulations to assess the impact of potential failures. I'll be talking about Monte Carlo simulations further in the presentation. They have taken up two matrix multiplication algorithms as a case study. One is the naive matrix multiplication algorithm, and the second is the Strasson's algorithm. They've used three error measures: Frobenius norm, or the matrix Euclidean distance, basically, and the infinity norm, and the logarithmic Frobenius norm, or the LFN. Coming to what the tool that they've developed, so the input to the tool is an written code or algorithm that you see on the left here. We need to define the error measures, we need to define the input generator, and we need to also annotate the code that needs to be tested, or where the errors need to be generated or inputted. And also we need to implement the failure method. So the first step is the calibration step, where the tool performs a calibration step to determine the maximum failure points and samples per failure points, which is FP and SPFP. After that, it moves on to injecting failures at different points within the algorithm and comparing the outputs of errorful and error-free runs to score basically the impact of each failure. So how critical each failure was based on the injected failures. Finally, the tool does a criticality assessment over here, which is visible on the right, and it shapes the failures. So it redistributes them and minimizes the overall damage. Moving to more depth and results of the Criticality Explorer, let me talk about what Monte Carlo simulations are first. Monte Carlo simulations are used to estimate the criticality of different failure points within an algorithm. So the process involves injecting failures at various points in the algorithm, running simulations to observe impact, and then analyzing the results statistically. If we have a closer look at this graph, we can see that the y-axis represents the criticality score. The x-axis determines the various failure points within the two algorithms. So the purple is the naive algorithm, and the yellow is Strassen. What is interesting to see in these graphs is that there is a high rate of failure at certain points in the Strassen's algorithm. So if there is a failure injected at these points, it critically fails. So you can see 1, 2, 3, 4 peaks, and which is quite consistent across the different error parameters. So the top row represents an n equal to 8, so 8 by 8 matrix multiplication. And the bottom row is for a 16 or 16 by 16 matrix multiplication. And another interesting thing is that the naive algorithm is basically unstructured. So there is a very flat and there are no peaks basically. So it indicates that the naive algorithm, the criticality scores are relative and uniform. And in the Strassen's algorithm, there is more significant spikes. Moving on to the case studies and the results. An interesting thing that the authors have introduced here is something called proxies. What basically a proxy is is that instead of assessing the criticality of every single operation in an algorithm, a simpler representation or basically a proxy is used to estimate the criticalities. This approach actually demonstrates that there is a similar reduction in the failures, but there is also a reduce in the computational effort that is required. An interesting point is that the data that the researchers have obtained had costed them about $320 in AWS fees to generate, because the Monte Carlo method is quite energy expensive. And once they introduced proxies, it costed them only about $13. So that's very, very interesting and a very good development. So we can see in this graph here, the x-axis represents the failure rate over here, and the y-axis represents the average error rate. So without any failure shaping or IID, which is independent and identically distributed failures. So the IID model was used as a baseline to measure criticality, and then they used direct failure shaping and followed by proxy failure shaping. So yeah, so that's for n is equal to 16, so 16 by 16, and there's the various error parameters that they use. So what I liked about this research was that the approach to handling the unreliable hardware was really refreshing, and they also implemented proxies, which was also really good in terms of energy efficiency and cost. What I did not like is that they use Monte Carlo, which takes a lot of processing power to get results. We can use better search-based algorithms like genetic algorithms or even simulated annealing to further cut down the costs. The application also was quite limited. They could have explored high performance computing or something with IoT or embedded systems to broaden the research area or the field. Those are my references. Thank you.